start. Good morning, everyone, to this morning session of the third day of the Copernican Congress devoted to the Anthropic principle. Actually, it was here 50 years ago during the big conference of the International Astronomical Union where Brandon Carter first presented what he called the Anthropic principle to our wider audience. And our today's panelists, Professor Berbard Carr and Professor Jean-Pierre Lassota-Hirschowicz, were both there to witness this announcement, this proposition of a new principle of cosmology. And it is my pleasure to introduce first Professor Berbard Carr, Professor of Mathematics and Astronomy at Queen Mary University of London. His area of research includes cosmology and astrophysics, in particular the early universe, primordial black holes, dark matter, and the anthropic principle, of course. He's also very interested in the role of consciousness, regarding it as a fundamental rather than incidental feature of the universe. And the plan of today's session is that first, Professor Carr will give a 50-minute talk, introductory talk about the anthropic principle, 50 years on. Then we will ask Professor Lassota to give his view on the anthropic principle, also 50 minutes, and the remaining time will be devoted to discussion, also with the participation of the audience. Professor Carr, the floor is yours. Thank you.
Thank you so much, Thomas. Well, it is a great honor to be addressing you today and be attending this wonderful meeting. But it's also very nostalgic for me because, as Thomas explained, I attended the meeting almost exactly 50 years ago in Krakow, where Brandon Carter gave his first major talk about the anthropic principle. So in some sense, this is the birthplace of the anthropic principle. I've shown there the abstract for the talk which Brandon gave. I won't read it all out because you can read it for yourself. But I'll just read out the last phrase. However, it is not inappropriate that this matter should have cropped up again on the present occasion, since it consists basically of a reaction against exaggerated subservience to the Copernican principle. So you can see there's, in fact, a slight tension with the idea of Copernicus in the anthropic principle, as we'll see. But the point about that meeting, of course, was that was the 400th anniversary of the birth of Copernicus. And so really, this is where the meeting where Brandon introduced the word anthropic principle in 1973. I should say that for a long time, the A word became rather unmentionable because it was rather unpopular in certain quarters in mainstream cosmology. So we would have to talk about the A word or the A principle. Now it's become much more respectable. But I should say that it wasn't actually the first meeting where Brandon spoke about it, because there was a smaller meeting in Princeton, which was in 1970. And I'll just read this out. The main idea of what I later called the anthropic principle were developed in a substantial DAMTP preprint entitled The Significance of Numerical Coincidences in Nature. DAMT was the Department of Applied Maths and Theoretical Physics in Cambridge. Now, this was circulated in 1967, so quite a bit earlier, in a stenciled form and belatedly placed on the archives 40 years later. So that's quite a long break, 40 years. Its first public presentation, entitled Large Numbers in Astrophysical Cosmology, was at the Princeton meeting organized in 1970. And you can see the meeting there. The people attending it, it was a small meeting. There is Brandon Carter himself. There is Stephen Hawking. And I won't go through all the names of all the various people here. Those of you who are cosmologists will know them all, but I think a lot of you are philosophers, so there's probably no point in highlighting the fact. But the point is there were some very eminent physicists at that meeting. Now, the abstract, this article itself, which appeared on the archives 40 years later, is shown here. I'm not going to read out the abstract, but you can see this is was a 40-year break between writing the paper and putting on the archives. Nowadays, physicists are very keen to put things on the archives within minutes of finishing their paper to get priority. But Brandon didn't worry about that so much. Also, this was only part 1 of his article, and he was going to publish a part 2, but actually we're still waiting for part 2, 50 years later. So, but really, it doesn't need to come because this has already started the field, and it's been a very active field, as we'll see. Now, I should say Brandon himself is 80 years on. He had his 80th birthday conference in Paris last July, sorry. And in fact, both myself and Jean-Pierre attended. I think you can see Jean-Pierre there, and I think I'm in the back. And it was a very special occasion. And obviously, we talked about the anthropic principle there as well, though Brandon did many other important things besides the anthropic principle. Now, I have to say, though, that the meeting in Krakow in 1973 was important to me in quite a number of ways. It's where I first met Jean-Pierre. But actually, what he probably doesn't know, the very first paper I read when I started my research was a paper by Demiansky and Lesota about black holes in an expanding universe. I don't know if you know that, Jean-Pierre, but so that was the first paper I ever read. And the first paper I ever wrote, I wrote with Stephen Hawking, and it was well, oddly enough, the title of the paper is obscured because it's I put the slide in the wrong position. But it was the paper I wrote with Stephen Hawking on black holes, primordial black holes forming in the early universe. And that was the first paper I ever wrote. And I gave my first conference presentation on that paper. It was actually in Warsaw, which was the preceding part of the meeting before we moved to Krakow. So for me, it was a very special occasion, not only because it was where I first heard about the anthropic principle, because it's where I first met Jean-Pierre and where I first gave my own conference talk, where I was very nervous. I guess I'm less nervous today. But so let me just say a little bit of introduction to what we mean by the anthropic principle. Of course, we're all used to the idea, the anthropocentric view, which says that man, and I should apologize, I've got man on these slides. By man, I mean M with a capital M, meaning humans. Not men as opposed to women, obviously. So we're all used to that we know that in for the Platonic view that the Earth was the center of the universe. We know that was the view, of course, which Copernicus famously overthrew. But that gave rise, that was soon replaced, of course, with Newton, with the mechanistic view. And in the mechanistic view, the universe is really like a great machine where the universe exists more or less independently of whether there's anybody here observing it. So the existence of man, again, humans, and mind is essentially irrelevant. The laws of nature would carry on as usual even if there was nobody here observing them. And that was the view which prevailed for 300 years, very much as a result of, well, the Newtonian view, at least the view which was initiated by Newton. Now, the anthropic view, though, says that some features of the universe are explained, and I say explained in inverted commas because it depends what you mean by the word explained, but are related at least to the requirement that life and mind should arise in the universe. The word anthropos is the Greek word for man, or we should say human. And that's where the term comes from. And that was the word that Brandon himself introduced. Brandon now regrets ever using the word anthropic because really these anthropic relationships I'm going to talk about are nothing to do with humans in particular. They're fine tunings, but to say that they're related to humans is very anthropocentric. So Brandon himself regrets using the term. Nevertheless, we're stuck with it now. I myself prefer to use another word. I like to think of this as a evolving complexity view. So I like to think of this as the complexity principle rather than the anthropic principle. The idea being we now accept the universe began with a Big Bang and 14 billion years ago, and throughout the history of the universe, we've had evolving complexity, which in some sense has culminated in brains, if you like, and consciousness. So that's just a sort of gentle introduction to what we mean by the anthropic principle. I'm really not sure how much people here are already familiar with it, so I don't want to labor the obvious. But now, I got into the game because I wrote a paper in 1979 with Martin Rees. Stephen Hawking was my PhD supervisor, but then after my PhD, I started working with Martin Rees. And we wrote this paper called The Anthropic Principle and the Structure of the Physical World. I'll just read out the abstract. The basic features of galaxies, stars, planets, and the everyday world are essentially determined by a few microphysical constants and by the effects of gravitation. Many interrelations between different scales that at first sight seem surprising are straightforward consequences of simple physical arguments. But several aspects of the universe, some of which seem to be prerequisites for the evolution of any form of life, depend rather delicately on apparent coincidences among the physical constants. And so really there were 2 points about this paper. The first point was to talk about the structure of the physical world, and that was purely straightforward physics, non-controversial. The controversial bit was the reference to the anthropic principle. Now this particular paper, it got quite a lot of attention because it was the first, Brandon, as I said, was the person who thought up the idea, but this paper got quite a lot of publicity because it was published in Nature and it brought a lot of the arguments together. On the other hand, it wasn't a very well-received paper in some quarters. A lot of physicists had a great antipathy towards the anthropic principle, regarding it as more philosophy or even theology. So that was in '79. Now, the situation has changed. It's still controversial, but a lot of very eminent physicists take it seriously, which is why, indeed, maybe you're here, because it's worth listening to. Now, so that's how I got into the game. But the various books, which I expect you've heard of, the first book, the big book, was by Barrow and Tipler in 1986. And John was a good friend of mine. John sadly died just about 3 years ago. So that was a very influential book. There's another more recent book called Fine-Tunings in the Physical Universe, which you may not have heard about. I mean, I have a chapter in there, but there are many other chapters, so I can recommend that book if you want to know more about it. I might say from my personal perspective, I was involved in a project which was funded by the Templeton Foundation, and this was in 2000. It was what's called the Cosmology and Fine-Tuning Program, and it was in collaboration with Robert Crittenden, Martin Rees, and Neil Turek, for a project called The Fundamental Physics and the Problem of Our Existence. And we organized a series of meetings. The first one was in Cambridge, 2001, Anthropic Arguments in Fundamental Physics and Cosmology. The second meeting was in 2003, was called Universe or Multiverse. And the third meeting was in Cambridge, 2005, Expectations of a Final Theory. And all of those meetings were written up in a volume, which I edited, called Universe or Multiverse. And obviously, I'd like to recommend that book, but it was interesting, and it was the first book to really bring together serious thinkers in the field from all different perspectives. Some of them were cosmologists, some were particle physicists, and there were some philosophers. And there's a question mark in the title because we were deliberately open as to whether there is a multiverse. I should say the multiverse, I'm going to come on to that shortly. The multiverse is the idea that there are many other universes and the constants are different in the universes, and this we'll see is relevant to explaining perhaps the fine-tunings. Now, there's the meeting. There's a photograph of the meeting in 2001. It was held in Martin Rees's back garden. I don't know if you're really interested. There's Stephen Hawking, and there are various key. There's John Barrow there. There's Martin Rees, who was hosting the meeting. George Ellis, myself. I mean, I think most of you aren't cosmologists, but the point I'm making is that these were all rather eminent cosmologists. And the very fact we were having this meeting was, in some sense, a sign that the subject was really being taken seriously. This was, by then, 30 years after Brandon and Carter first introduced it. But it's interesting to contrast the changing attitudes to the fine-tuning problem. And these are quotes from that book. Frank Wilczek, who was a Nobel laureate, he said, the previous gathering, by which he meant 2001, had a defensive air. It prominently featured a number of physicists who subsisted on the fringes, voices in the wilderness who had for many years promoted strange arguments about conspiracies among fundamental constants and alternative universes. Their concerns and approaches seemed totally alien to the consensus vanguard of theoretical physics, which was busy successfully constructing a unique and mathematically perfect universe. Now, that means the 2005 meeting, the vanguard has marched off to join the prophets in the wilderness. So even in 5 years, there was a big change in the subject becoming respectable. And that was because eminent physicists were getting involved. The other eminent physicist was Steven Weinberg, another Nobel laureate. And a lot of people objected to the anthropic principle on the grounds that they didn't think it was proper science. What Steven Weinberg said, he said, we usually mark advances in the history of science by what we learn about nature, but at certain critical moments, the most important thing is what we discover about science itself. These discoveries lead to changes in how we score our work in what we consider to be an acceptable theory. Now, Weinberg had introduced an argument associated with what's called the cosmological constant for believing in the anthropic principle. But this was making a more general remark. And it's important to realize that the reason people take the anthropic principle, at least quite a lot of physicists take it seriously today, is simply because of the eminence of some of its proponents. I mean, besides Brandon, people like Martin Rees, Steven Weinberg, Frank Wilczek, Leonard Susskind, Stephen Hawking. And in science, what is respectable tends to be determined by the opinions of a relatively small number of people. And I know there seems to be an interest in the sociology of science, so I think that's quite important. So, as I said, when I wrote the paper in 1979, and when Brandon introduced the idea in 1973, it was a minority interest, very controversial. I would say today it's not exactly mainstream, it's still controversial, but at least maybe 50% of cosmologists are prepared to talk about it. Now, the first point to make is that I'm going to talk about fine-tuning, but there are different types of fine-tuning. And it's important to distinguish between them. Now, the first type of fine-tuning involves natural coincidences between the various scales of structure in the universe. Now, I'm going to show a figure now, which might look a bit complicated from my paper with Martin Rees. I don't know how many people are physicists in the audience, so I'm going to use a few equations. So if you don't understand equations, just close your eyes. But none of them are very complicated. But the point about this diagram was that it was a plot of mass against length scale, and of all the various things that exist in the universe on various scales. We've got protons and atoms, we've got black holes, we've got planets and stars and the galaxies of the universe. And the scales are in grams and centimeters, but what's really important about this diagram is that all of these scales can be predicted in terms of basic physics. And they just depend upon two constants. One is called the fine structure constant, which determines the strength of the electrical interaction, and that's basically 10 to the minus 2. It's 1 over 137, one of the most famous constants in physics. The alpha G is what's called the gravitational fine structure constant, and that's the gravitational force between two protons as opposed to the electric force. And that's something like 10 to the minus 40. And the fact that the gravitational fine structure constant is so much smaller than the electric fine structure constant merely means that the gravitational force between two protons is tiny compared to the electric force. But on large scales, objects are electrically neutral. So obviously, I'm not going to go through the arguments, but that's non-controversial. These arguments are non-controversial. But for example, what you get from that, again, apologies for the equations. I was told they're mathematicians in the audience, so at least I can use equations. But so, for example, all those scales, I've just written down what was in the diagram. You can express the mass in terms of the proton mass and the size in terms of the size of an atom, in terms of alpha and alpha G, and those are the sort of relationships you get. And you then get interesting coincidences. For example, the mass of a human being, now I'm saying a human here, I'm glad I got it right this time, is the geometric mean of the mass of an atom and the mass of a planet. And the point is, you might think that's a coincidence, but it's not. It comes out of basic physics. I mean, obviously, this twiddles means it's not exactly. It's like to a factor of 2 or 3. Because we're not obviously all the same mass, but we are roughly the same mass. The number of galaxies in the universe is alpha to the minus 6. The number of stars in a galaxy is a more complicated, alpha to the 4th times alpha G to the minus a half. So all of this was really interesting from a physical point of view and non-controversial. I want to show my favorite diagram in physics. In fact, I'm going to give a whole talk about this at the festival. It's the cosmic Ouroboros, which is the snake which swallows its own tail. And the point about this is that it's like a rule, a scale of structure. And as you go from all the various objects which exist in the universe can be placed around this Ouroboros. So we got people at the bottom, and as you go to bigger scales, I should say that as you go from the top left all the way anti-clockwise to the top right, the scale increases by a factor of 10 for each minute, if you like. So it's like a clock. And you've got people at the bottom, and then on bigger scales, you've got mountains and planets and stars and solar systems and galaxies and the cosmos. On the left, we've got progressively smaller things like ants, amoebas, DNA, atoms, nuclear particles, and then at the very top left, we've got what's called the Planck scale, the smallest scale you can have in physics. So I just love this diagram because it summarizes all we know about the physical world. It summarizes the triumph of physics. But what's interesting is that you can write these scales in terms of the fine structure constant, which remember is roughly 10 to the minus 40. And because alpha G is 10 to the minus 40, the number of decades of scale is alpha G to the minus 32, so it's 60. So it's just a nice little coincidence. It's like a clock. And the reason because it's got 60 minutes, if you like, and that's because alpha G is 10 to the minus 40. But then you might want to ask the question, why is alpha G so small? And one little clue is that the number of stars in the universe is alpha G to the minus a half. Now, the anthropic principle is to do with the development of life. Now, we know most star systems are not going to have life because that's going to depend on some probability, which may be very low. I think maybe Jean-Pierre will talk about this topic. I'm not certain. But the point is, the probability is very low, so you need lots of stars if you want life to arise somewhere. And so if the probability of life is we call that P, then alpha G must be less than this probability squared from this formula. So that's one qualitative explanation of why alpha G must be very small. But the point is that even if alpha G were different, even if gravity was stronger or weaker, this diagram would still be true. It would just have a different value of alpha G, a different number of minutes around the clock, if you like. So I'll come back to that diagram later on. But then the interesting thing, you might ask, Why does the head meet the tail? That's the key of the symbol. The snake is swallowing its own tail. And that's to do with cosmology, because in the Big Bang theory, the Big Bang is associated with the top. And the reason for that is that in astronomy, your information travels at the speed of light. So if you see a galaxy a million light years away, you're looking a million years into the past. So the universe began with a Big Bang 14 billion years ago. So if you look to a distance of 14 billion light years, you're looking back to the universe when it was very, very, very small. So that's why the Big Bang is associated with this, that's where the very large meets the very small. And so there is that is the image, if you like, associated with the top of the cosmic Ouroboros just there, where the very large meets the very small. Also, that's where quantum theory meets relativity theory. We know relativity theory and quantum theory work with amazing precision in the microscopic and macroscopic domains, but they're not compatible with each other, and the great dream of physics is to get a theory which combines them, and that theory will be manifested at the Big Bang. And because of the Big Bang, cosmologists now have a very good understanding of the history of the universe. It starts off the left with the very compressed state, and then I'm not going to go through this in detail. I'm sure you probably know, you've heard this many times, but basically you have various key phases in the early universe. We have what's called nucleosynthesis. You then have what's called the dark ages. Then you have galaxies forming, and then eventually we form, and we look back on the beginning of the universe. But I don't want to talk too much about that because I'm just giving a brief overview. Now, what I've talked about so far is conventional physics and conventional cosmology, and I should explain cosmology as my professional area. Now, a different type of fine-tuning is to do with selection effects on when and where observers exist. And this is called the weak anthropic principle. And I'll give you a simple example of this. Why is the universe as big as it is? I said the universe began with a Big Bang. Well, the mechanistic argument is that the time since the Big Bang is 10 to the 10th years, so the size of the observable universe is essentially 10 to the 10th light years, the distance light has traveled. So there's no particular reason for that. It just happens to be that's the age of the universe. But this was the anthropic view, which was actually an argument given by Bob Dicke actually in the 1960s. So this was before Brandon's work, in fact. And Bob Dicke said, well, life requires heavy elements. And those heavy elements have to be made in stars. And then the stars explode as supernova, and those heavy elements eventually get incorporated in planets and people. But the point is that there will be no life, there will be no heavy elements before stars had burnt out. And that, roughly speaking, is a lifetime of 10 to the 10th years. For our sun, at least, the lifetime is something like 10 to the 10th years. Bigger stars have a shorter lifetime. But on the other hand, if you waited much longer than 10 to the 10th years, then there wouldn't be any stars left, so there wouldn't be any life either. So this is basically saying the only time when life can be around is roughly 10 to the 10th years after the Big Bang, which meant its size is 10 to the 10th light years. And so basically, this explains why the age of the universe, if you ask what the lifetime of a star is in terms of physical constants, it turns out to be alpha g to the minus 1, which is 10 to the 40 times the proton times. The time scale associated with the proton is 10 to the minus 23 seconds, but it's basically 10 to the 10th years. It also means the number of protons in the universe is alpha g to the minus 2. So these were all famous coincidences which are explained by this argument. So that's the weak anthropic principle, and really it's not controversial. It's just a logical necessity. It's saying that our existence imposes a selection effect on when and where we exist. Just as life probably has to exist near a star, it's a selection effect in space, it also has to exist at a special epoch, according to this argument. Now, there's the third type of the anthropic, of the fine-tuning, is saying that the physical constants themselves, in some sense, need to be fine-tuned in order for there to be observers. So the weak anthropic principle is saying, given the laws of physics and the constants of nature, there is a selection effect on when and where life can arise. This is saying there's a selection effect on the values of the constants themselves. And this is much more controversial. This, at least, is the sense in which myself and Martin and Brandon Carter use the term strong anthropic principle. Notice that if you believe in the multiverse, which I haven't said much about yet, if there are many universes, in some sense, the strong anthropic principle just becomes an aspect of the weak anthropic principle, because it's just saying we have to be in one of the universes which has suitable constants for life. Now, what constants am I talking about? Well, there, of course, are many constants in physics. Don't try and read all these. I just want to give you some impression of what physicists mean by physical constants. The first set of constants, they're associated with particle physics and the forces of nature. The second set of constants are associated with cosmology. I'm a cosmology. But the question is, which of these constants are fundamental and how many of them are independent? And we don't know for sure the answer, but it's clear that some of these constants are related to each other. But at this point, I should say that in terms of particle physics, the great achievement of particle physics is to show that the various forces of nature can all be unified and to be part of a sort of an amalgamated force. And I think you're probably aware of this, but for example, electricity and magnetism, they were unified into electromagnetic theory by Faraday and Maxwell. Then the weak force, which operates on the atomic scale, that was unified with the electric-magnetic force to form the electroweak force in the 1970s. That's a topic Weinberg got his Nobel Prize for. There's the strong force, and the strong force actually, in theory, can be unified with the electroweak force to form grand unification, sometimes called the gut force, grand unified theory. And then, of course, the real dream is to amalgamate all these with gravity. And the amalgamation with gravity, we don't know yet, but some people like the idea of M theory. Well, I don't want to go into the details of these theories, but the point is that the dream of physics is to have this unified understanding of all the actual forces of nature. And in fact, I think Michael Heller showed a diagram like this on the first day, showing how these forces are unified. And if they are unified, in some sense, you can probe them by looking back to the early universe, because you go back to the early universe, the temperature gets higher, and you in some senses see all these unifications occurring at early times. But the question is, have we got the theory of everything? Physicists would like to say we're close to a theory of everything. We don't know it's M theory. Not everyone believes in M theory. But that's the great aim. But the question is, when you've got your theory of everything, how many fundamental parameters will be left? In the old days, even amongst M theorists, the hope would be there will be nothing. All the physical constants will be explained by your theory, your M theory. But unfortunately, it no longer seems like that. In fact, some M theorists now talk about having 10 to the power 500 theories with versions with different constants. But that's the big question. Now, if we go back to this, my favorite diagram, the cosmic Ouroboros, these forces are interesting because they link the left side of the diagram, the microscopic domain, with the right side, the macroscopic domain. And I can explain why. For example, the same electric force which determines which holds the electron in orbit around a proton determines the structure of solid objects. The same strong and weak forces which operate inside nuclei also determine nuclear burning in stars. The electroweak force may be associated with the dark matter, which we observe around galaxies. The granularified force may have some connection with the fluctuations which eventually turn into galaxies and large-scale structure. So you can see that the forces of nature, they provide a sort of vertical links in this cosmic Ouroboros. I hope this isn't getting too technical for people, but I'm trying to get it. You can always ask me later if I can explain something better. So in some sense, the Big Bang right at the top is the culmination of this macro connection. And there we've got M theory in the multiverse right at the top. Now, but let's look at these dimensionless coupling constants. They're each, the coupling constant is dimensionless, and it's normally symbolized by alpha. So for the gravitational force, I've said it's roughly 10 to the minus 40. The electric force is 10 to the minus 2. You should also know about the weak force, which is about 10 to the minus 10. And the strong force is 10. And it's called the strong force because it's larger. But those are dimensionless numbers. And so a lot of these anthropic tunings involve these coupling constants. And I don't want to get into technicalities, but I'll give you some examples. But the question is, will the final theory of everything explain these values? The hope was always yes, but in practice, the answer seems to be no. Certainly so far, they haven't done so. So these constants seem to be contingent. Now, I'll just give you two examples. Again, apologies if this is too technical, but some of you may appreciate it. All stars have a mass of alpha g to the minus 3 halves, I should say, times the proton mass. That was one of the relationships I mentioned right at the beginning. But also, there is another division between stars which are called convective and radiative. This refers to the way in which the heat generated in the core by nuclear reactions gets out to the surface, either by convective processes or by radiative processes. And it turns out that that mass looks like this. I'm sorry to have so many equations here, but it's just to try and get it across. Now, the only reason stars exist with both these characteristics is because this mass scale is roughly this mass scale, and that's because alpha g is the 20th power of the electric fine structure constant. Now, and Carter basically pointed this out. This is true because if I take the 20th power of 10 to the minus 2, I get 10 to the minus 40. But who would have guessed that that was a condition you require to have both convective and radiative stars? And you do need both types of stars. The convective stars are the ones which may be associated with planetary formation. The radiative stars are the ones which may evolve into supernova. So apologies if that is too technical. Sorry, there's the image of the Eagle Nebula where stars are being born. Now, supernovae, when a star collapses at the end of its evolution, the envelope can be blown up as a supernova. And the reason that happens is because neutrinos get generated in the core, and the neutrinos can blow off the outer envelope. But that only happens because there's a fine-tuning between alpha G and alpha W, because alpha W is determining the strength of the weak interactions. Well, again, that relationship is true. The 10th power of 10, the 4th power of 10 to the minus 10 is 10 to the minus 40. But nobody knows why. Now, it's also, and so there's a picture of the Crab Nebula. This is also related to Big Bang nuclear synthesis, but I won't get into that. That would be too technical. The point I want to say is these relationships are required for life, but they're not explained by current physics. They weren't at the time of Brandon Carter's argument 50 years ago, and they're still not explained by current physics. So those are just some examples. Now, there are other famous examples. I'm not going to go through all of these. This is the famous triple alpha coincidence pointed out by Fred Hoyle. In order to have carbon, and life is based on carbon, you have to appeal to what is called the triple alpha reaction. And that means that, first of all, two helium nuclei combine to form beryllium, and then the beryllium combines with another alpha particle, a helium nuclei, to form carbon-12. Now, the trouble is that normally that reaction wouldn't occur because the beryllium would decay before it could find another alpha particle to make carbon-12. However, it turns out that there's a special nuclear resonance which allows this reaction to occur. And Hoyle was able to predict that resonance. And they looked for it and they found it. So this was in some sense an anthropic prediction. Because the beryllium would decay too soon if it weren't for this fine-tuned resonance. So, and that means you're fine-tuning to something like 0.1%. The strong interaction to something like 1%. Now, there are lots of constraints from chemistry. Again, I'm running a bit out of time, but I'll just go through these quickly. If the alpha F, if the strong constant was increased by 2%, all the protons in the universe would go into diprotons, that's 2 protons, at the time of Big Bang nucleosynthesis. There would then be no hydrogen-burning stars, and you need hydrogen-burning stars to have a long lifetime. If it was increased by 10%, all the protons would go into nuclei of unlimited size, and there'll be no interest in chemistry. If it was decreased by 5%, all the deuterons, the protons and neutrons, will be unbound. And that would mean you'd only have hydrogen. And you wouldn't have interest in chemistry. Because basically chemistry depends upon the fact you've got a balance between the strong interactions, which hold the nuclei together, and the electric forces between the nuclei, which are trying to pull them apart. There are other constraints which involve the masses of the elementary, of the various. Again, I'm sorry if there are too many equations here, but it involves the masses of the neutrons and the protons and the pions and things like that. But suffice it to say that alpha S is also fine-tuned. In fact, everything seems to be fine-tuned. So in terms of my favorite diagram, essentially you've got, if you like, microphysics on the left, macrophysics on the right. Here you've got mesophysics, which is human beings in between. And the fine-tunings are to do with the vertical links in this diagram. So I showed you before the horizontal links representing the forces of nature. The fine-tunings are saying there's a vertical link in this diagram. Now, how are people reacting to this? Well, and these are the early reactions. Here's Freeman Dyson. I do not feel like an alien in this universe. The more I examine the universe and examine the details of its architecture, the more evidence I find that the universe, in some sense, must have known we were coming. Heinz Padgel, though, he was against the multiverse. Sorry, against the anthropic principle. I've not yet used the word multiverse. The influence of the anthropic principle on contemporary cosmological models has been sterile. It has explained nothing. It has even had a negative influence. I would opt for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science. And he was probably representing the majority view at the time. Here's Brandon with his middle way. The anthropic principle is a middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. So that's the view which he espoused here in Krakow, and that's the view I would say, which I think is the correct view. A lot of people would accept as the correct view now. Now, there are also, Thomas, I started 5 minutes late, is that right? So I've got another 5
yes.
minutes. Right?
Yes, indeed.
Okay, so there are also a lot of constraints associated, anthropic constraints associated with cosmological parameters. Now, again, these are a little bit technical, but Martin Rees, who was another person who's been a prime advocate of the anthropic principle, he wrote a book called Just Six Numbers, which was talking about the various cosmological parameters which seem to be fine-tuned. Some of them I've already talked about. The ratio of the electrical and gravitational force, that's the ratio between alpha and alpha G. The strength of nuclear binding I've also talked about. These other parameters are very important to cosmology. The density parameter, how much matter there is relative to the density required for the universe to recollapse. The cosmological constant, Q, is the amplitude of the fluctuations which are required to generate galaxies. We know that's about 10 to the fifth, and another one is the number of spatial dimensions. Now, I did have some slides on this. I think I'll just go through them very quickly because they may be too technical. I'm running a little bit out of time. The density parameter, in cosmology, if the density is high enough, the universe recollapses, otherwise it expands forever. And we use a parameter omega, which is the ratio of rho to the critical density which divides them. And the point is, if omega was too large, the universe would recollapse too soon, there'll be no life. If omega was too small, the fluctuations would never develop into galaxies. So we always knew at this time that omega had to be between about 0.1 and 10. Later on, inflation came along and explained that why omega was 1, but even that requires fine-tuning. The amplitude of the fluctuations, again, this may be too technical, but if the amplitude is too small, then the gas cannot collapse into gravitational bound structures. If it's too large, bigger than 10 to the minus 3, regions collapse into big black holes rather than stars. So there's fine-tuning on the value of Q, but we can't predict the value of Q. This is a diagram. Sorry, that's too technical, so I'll miss that out. The cosmological constant, perhaps the most interesting one, in the 1990s we discovered the universe was accelerating, and this is normally explained by invoking a cosmological constant, which Einstein had originally predicted. Now, the problem is that the value of the cosmological constant observed was actually far too small. It was 120 orders of magnitude larger than expected. Sorry, that should say smaller. I've made a typo. The value of the cosmological constant, the density is so, it's got units 1 over length squared, and actually it's observed to be 10 to the minus 56. Okay, but actually, in theory, should be 10 to the 66. Well, actually, sorry, this is fine as it is. It depends if you talk in terms of the density or the value of lambda itself. But the density is 120 orders of magnitude less, but the actual constant itself is 120 orders of magnitude larger. So that is okay. And the point is, the galaxies can't form if that was too large, because the cosmological constant prevents galaxies forming, and that's what Weinberg pointed out. And you get constraints on the combination of lambda and Q. Now, that cosmological constant was very important because the same it's saying basically that the universe's energy is dominated by this mysterious dark energy, which we don't really understand, but it's probably associated with the cosmological constant. But what's really interesting is that the same cosmological constant, which is explaining the dark energy, is also meant to be present in the early universe and generating inflation. And inflation is a period in which the universe is expanding exponentially fast, rather than by a simple power law. And for various reasons, cosmologists like this. It explains a lot of cosmological mysteries. And for example, inflation predicts fluctuations which generate galaxies. And though when they measured the microwave background temperature fluctuations, it fitted exactly what was predicted. So cosmologists really rather love the inflationary theory. But what's important about inflation is that it predicts that our visible universe is only a small part of a much larger reality. There are many different versions of inflation, but roughly speaking, we are just part, if you like, of one bubble, and there could be many other bubbles. And this is the idea of a multiverse, that our universe is just one of many other universes. And in a certain sense, one shouldn't be too surprised by the idea of a multiverse. Physics wants to explain everything. We know there was a Big Bang, but we want to understand the physics of the Big Bang. If you've got a physics which is going to produce one Big Bang, presumably it can produce many Big Bangs. So in principle, it's not a crazy idea that physics might predict many versions of the multiverse. But the point is there are many different versions of the multiverse. And I'm not going to go into the scenarios for the multiverse because it's a whole topic in itself. Let me just say that there are many models within cosmology, cyclic models, turn inflation, even brane models in higher dimensions, and models of particle physics, quantum many worlds, string landscape, quantum cosmology, which produce the multiverse. So the point is the multiverse may be controversial, but it is in fact a standard prediction of both cosmology and particle physics. And the reason why that's relevant is because, as discussed in the book, Universal Multiverse, recent developments in cosmology and particle physics suggest that our universe, rather than being unique, could be just one of many universes. Since the physical constants can be different in other universes, the fine-tunings which appear necessary for the emergence of life may be explained. So this is linking the multiverse to the fine-tunings. And not everyone believes it, but it is at least a natural explanation of this. So I just want to then finish up, because this will lead into Jean-Pierre's talk, to talk about the explanations for the fine-tunings. Well, the first explanation is the one which I've talked about, that there is a multiverse. The second explanation is that it's more philosophical. It says, well, maybe consciousness, in some sense, collapses the wave function. In quantum theory, the question is what collapses the wave function? And one theory is that maybe consciousness collapses the wave function. So you could say, well, the universe begins with the Big Bang, and it evolves, it produces galaxies and planets and people who then develop consciousness, and in some sense, think about the Big Bang, and it produces a sort of closed circuit, and the universe comes into existence. But of course, the other explanation, if you're of a religious disposition, is to say, well, maybe God, maybe there's some tuner who chose the constants in order that life can arise. Now, theologians like that, but of course physicists don't like that. And this is one reason, I think, why the anthropic principle was initially so unpopular among physicists. They didn't want to invoke God. Now, and so you might say that this is physics, this is metaphysics, and this is theology. But even though as a physicist I'm favoring multiverse, that's not to say I'm correct. You've still got these different types of explanations, and maybe this will come up in the discussion. But the other thing to bear in mind is that the opinions differ as to where the boundary is between physics and metaphysics, for example. For example, some people think that the multiverse is metaphysics. Some people think the multiverse is just as inexplicable as God, so that's metaphysics. And maybe quantum collapse by consciousness is theology. And then instead you will have the universe is so... This is the sort of Stephen Hawking view, in the universe in a nutshell. The universe creates itself. There's only one universe. And physics explains everything. And all I will say in response to that is that actually the distinction between cosmology and metacosmology, which may well be a focus of the discussion later on, is very fuzzy. There's a huge debate about whether the multiverse and the anthropic principle is respectable physics, or whether is it just philosophy. And I take a view that it's on the border of the two. It's what I call metacosmology, and we might get onto that later. So I think I'm now, obviously it raises the whole question of what do we mean by an observer? And again, I think Jean-Pierre is going to address this. I've not defined, we've said that the universe is fine-tuned, but what is it fine-tuned? Is it fine-tuned to professors of mathematics, or is it just fine-tuned to humans, or a mouse, or a robot, or just some physical process? It's really completely ambiguous. Sorry, this slide comes from Max Tegmark. That's a mouse, not Max. And as I said, for me, the crucial thing is that these fine-tunings are required for complexity to develop. You can, in the history of the universe from the Big Bang, it's clear that you're getting ever more complex structures. It forms like a pyramid. And in some sense, living organisms and brains and things are at the top of the pyramid. So in some sense, it's the culmination of complexity. So I think of it as a complexity principle. And the point is, in order to generate this pyramid of complexity, you need to have all these fine-tunings I've talked about. So from that perspective, the precise criterion may not be so crucial, because it may be that once the pyramid starts, you soon end up with consciousness anyway. So just to end, the question is, when you've got your fundamental theory, is the fundamental theory going to uniquely determine all the constants of physics? If so, there is no room for anthropic reasoning. If, however, you've got a multiverse that you can have universes with different constants, then necessarily our existence will require that be in one of the anthropically selected universes. And so that's what it all comes down to. What is the nature of your final theory? And so going back to my diagram, my favorite diagram, quantum theory on the left, relativity theory on the right. Our final theory is up at the top along with the Big Bang. The question is, will the marriage of quantum and relativity theory elucidate the fine-tuning? And in other words, will it have something to say about consciousness? And I'll just end with this slide. This is my favorite picture of Einstein in his dressing gown. I found during the pandemic, I spent a lot of my time in my dressing gown, so I like this diagram. What really interested me is whether God had any choice in the creation of the world. And but I would like to, because we're really celebrating Brandon, I'm replacing Einstein's head with Brandon's head. And I'd just like to say happy 50th anniversary to the Anthropic principle, and thank you.